All right. Good morning, everyone. Good morning. 8:30. Let's go ahead and get started. I do want to finish up with the vasculature this morning. I have a couple of games that we're going to play today, so I do have prizes. That'll help with the review session. Also, there's a formal review session today between 4 and 6 in B45 Rutan Hall. B45 Rutan Hall. Between 4 and 6, okay? I will record the session. There's already a recorded session online if you haven't seen that yet. And you can go ahead and take a look at that just in case something happens with the recordings. So far, we've been doing pretty well, so I am recording this session as well. So let's get started. I want to just, I kind of skipped around last Friday, so I want to start here. I know we've already kind of taken a look at this diagram, but let's revisit it. All right, so I just want to make sure that everyone realizes that the arteries actually have these profound elastic properties. So you can see there's a lot of musculature that is surrounding each of these arteries. And you can even see here, this is a muscular artery. They each have their components. You can actually see the inside of the tube are the endothelial cells. That's the blood vessel cells. And then there's smooth muscle that actually surrounds it. Again, arteries are very elastic. So like a balloon, if you force blood into it, it's going to stretch, and then there's going to be a recoil effect, okay? And as we talked about before, I'll just go to this next one here. You can actually see the arteries act as dampeners. So because of that elastic recoil, you can see that it actually dampens the fluctuations, those oscillations. And again, it's important because it keeps the blood moving even when the heart is in diastole. Okay, so even when the heart is relaxed, because of the elastic recoil effect in the arteries, it keeps the blood moving even in diastole. All right, so going back to the previous slide here, I want to make sure you remember that arterioles are, there's extensive branching from the arteries. The arterioles don't have as much musculature, but you can actually see the smooth muscle that surrounds the arterioles. The thing to remember about arterioles is that arterioles are a dynamic site of regulation. So there's a lot of input from neurons, from local environments that causes vasoconstriction and vasodilation within the arterioles. Then these tubes continue to branch. We'll talk more about the capillaries today too, venules, and then veins hardly have any elastic property. I almost call them like floppy tubes. There's no elastic recoil effect at all. All right, so let's start from the beginning here. Just wanted to give you a few more details about each of these tubes. Let's go back to the elastic arteries, then we'll get into the arterioles. All right, so we're back here at the elastic arteries. Let me just give you some information about the sphygmomanometer. Sphygmomanometer is a fancy name for blood pressure cuff. And to estimate the systolic and diastolic pressures, what you do is you put the blood pressure cuff over your arm, your biceps and triceps, and what it's doing is it's measuring the fluctuations in the brachial artery, okay, the brachial artery. And this is basically how it goes. You do have this animation on your Canvas website. All right, so we'll take a look at it here. Sphygmomanometry. Whenever you see manometry, that's a measure of pressure changes. So what you have here, again, is the blood pressure cuff. Usually put it on your arm. You also usually have a stethoscope. So if you go into the clinic, nurse uses both equipment. And you can see that normally the blood pressure ranges, this is kind of a normal pressure, between 120 millimeters of mercury and 80. And this is how it works. What you do is you inflate the cuff, and the pressure in the cuff, you usually inflate it until it's above any kind of systolic pressure. When you reduce the blood pressure cuff, what this does is at first it's blocking the brachial artery, right? So there's no flow through the brachial artery. Then you reduce the cuff, and then you should be able to hear sounds here. Okay, I'm going to just stop this for a minute. The sounds are, you can hear turbulent flow, but you can't hear laminar flow. So when your blood is flowing through the tubes, usually it's laminar flow, it's very silent. But if you block the brachial artery and then you start to allow blood to flow through, like you see here, it causes turbulent flow, which you can hear with the stethoscope. Turbulent flow is very loud, and that's what you're hearing here. As soon as you release a little bit of blood into the brachial artery, you can start to hear that turbulent flow. All right, so what you do then is you can reduce the blood pressure cuff even more. Those sounds get longer and longer, that turbulent flow, until they're very long, relatively speaking. And then once the blood pressure cuff, the pressure in the cuff falls below the diastolic pressure, then it returns to laminar flow and it's silent. And then you can figure out that diastolic pressure. So as soon as you start hearing sounds, you can mark that as the systolic pressure. And as soon as you reduce the pressure in the cuff so that you don't hear any more sounds, then you can mark the diastolic pressure. So that's how a sphygmomanometer works. And you can take a look at this again on your own at home. So sphygmomanometry, remember that is capturing the systolic and diastolic pressure in the brachial artery. So moving to the arterioles, we also talked about this last time. I talked about the difference between tubes in series and in parallel. The arterioles are arranged in parallel, and blood flows to various organs which can be altered. Again, this is a dynamic site of regulation. It can be altered by extrinsic mechanisms. This is coming from the outside of the local environment. That includes the nervous system, like the sympathetic nervous system, or the endocrine system, many different hormones like vasopressin or angiotensin. We're not going to get to that until we talk about the kidney, but these are hormones that can actually cause vasoconstriction. Vasopressin, angiotensin, even the name suggests vasoconstriction. And then intrinsic mechanisms, those include the metabolic state of the tissue. So if there is a drop in oxygen or an increase in carbon dioxide, that will signal the smooth muscle cells to vasodilate so that more oxygen can actually be brought into that area. So again, the arterioles are a dynamic site of regulation. And we talked about this last time as well, Poiseuille's law. I always butcher any kind of French name here, but this is giving you an idea of the resistance terms. And the take-home message here is small changes in the radius of the tube, because of that r to the fourth power, translates to huge changes in resistance. Now, we didn't talk about this slide, so I want to make sure that I cover this. So this tank right here is symbolizing a pressure reservoir, or the mean arterial pressure, right? Mean arterial pressure equals flow times resistance. And this is symbolizing the mean arterial pressure. Your body does a really good job of maintaining mean arterial pressure within a specific range. And so you can see here the arterioles are represented by these outflow tubes. Some have a very high resistance. You can see a lot of vasoconstriction happening. Some don't, vasodilation. So there is a large amount of flow to organ number 2 here. So in order to maintain this pressure reservoir, if, let's take a look at organ number 2, if vasoconstriction occurs and flow is restricted to organ number 2, there has to be a compensatory change. There has to be a change in a different organ. In this case, it's organ number 3 that now has vasodilated and the flow has increased to that particular organ. Otherwise, you can imagine this delta P, the mean arterial pressure, is going to change. If we didn't increase the flow to organ number 3, then mean arterial pressure would increase too much. So usually dynamic adjustments in the blood distribution is accomplished by relaxation and contraction of circular smooth muscle. And if you change flow to one organ, you have to change the flow to another organ in order to maintain this pressure reservoir, mean arterial pressure. Okay, so we've talked about the metabolic activity, these intrinsic mechanisms that can cause vasodilation. And you don't need to memorize this, but these are just some examples of extrinsic and intrinsic mechanisms that can alter arteriolar radius. Okay? So sympathetic neural controls include sympathetic nerves like we talked about, hormonal controls, some examples are vasopressin and angiotensin, which I mentioned, and then local controls include a decrease in oxygen, increases in carbon dioxide, and the like. So that's more or less of a review slide. And then when you look at what happens in the arterioles, this is giving you an example of downstream pressures and flow rates. So this is blood pressure, but remember this is downstream of the arterioles. Vasodilation, that keeps blood pressure fairly high. But any kind of vasoconstriction restricts flow and causes a plummet in the blood pressure downstream from that arteriole. Okay, and again, compensatory changes in arterial resistance occur to protect mean arterial pressure, as we just talked about. Okay, so jumping to the capillaries, we have already gone through this slide. I do want you to know the differences between continuous, fenestrated, and sinusoidal. In a nutshell, continuous capillaries, they have very tight junctions and they don't allow for a lot of leak. But on the opposite extreme, sinusoidal cells are held together by very few tight junctions and they're very porous. When we get to the kidney and we talk about the glomerulus, the nephron and the glomerulus, those happen to be fenestrated cells, fenestrated capillaries. So it allows for plasma, right? Kidneys are all about filtration. And so they filter your blood, and those capillaries are called fenestrated capillaries. And we'll talk more about that when we get to the kidneys. So capillaries are very tiny tubes. This is kind of a nice image because you can see it only allows red blood cells to go through the tubes in single file. They're so small, and they're very thin to allow for a lot of oxygen and nutrients to be exchanged. So when we talked about the velocity, this should also be reviewed, the velocity of blood flow through the capillaries. Remember, you have to take the entire surface area of all of the capillaries together. So the surface area increases tremendously in the capillaries because of all the branching and all the capillaries in parallel. And with that, there's an inverse relationship between area and velocity. What that should tell you is the velocity plummets in the capillaries. It's very slow. Again, allowing enough time for oxygen and nutrients to be exchanged at that site. Okay, again, very tiny, thin-walled cells. Velocity is very slow, and that makes the capillaries the primary point exchange between blood and the interstitial fluid. And the interstitial fluid is what the fluid that bathes cells within that tissue. Okay. So again, remember the capillaries are in parallel with each other. This is actually one of the more important concepts today. I want to talk about net filtration pressure. And you will have a calculation on your exam on Wednesday, but it's very simple. It's all about addition and subtraction. It's not a very complicated equation. So what it is, first let me just give you some information about filtration and absorption. So like I just said, there's a lot of exchange in the capillaries, okay? This diagram is symbolizing what's inside the capillaries. This is inside the tubes. You've got all this plasma. And this light blue box is representing the interstitial fluid, which is outside the capillaries. So, anytime you are pushing fluid out of the capillaries, that is called filtration. So the movement of fluid and solutes out of the blood, out of these capillaries, is called filtration. Anytime you're drawing fluid into the capillaries, that's called absorption. Movement of fluid and solutes into the blood is called absorption. So, this is on your equation sheet. This is called net filtration pressure. It's also called Starling forces. So again, it's named after Frank Starling. Actually, I'm sorry, it's not Frank Starling. It was two scientists. It was Otto Frank and Ernst Starling. So these are called the Starling forces, Ernst Starling, Starling forces, and basically what it takes into account is the net hydrostatic pressure, that's the P here, net hydrostatic pressure. And let me just give you an example so you know what that means. Hydrostatic pressure is if I had a cylinder, right, and I had fluid in it, and I had a piston, and I started to push on the piston, I would increase that hydrostatic pressure. So it's kind of a mechanical pressure. So you're talking about the hydrostatic pressure in the capillaries and the hydrostatic pressure in the interstitial fluid. Okay? Now, pi, if you remember, we talked about osmotic pressure a long time ago. Pi is representing something called oncotic pressure, which is the osmotic pressure of the larger blood proteins. So, pi is oncotic pressure, which is the osmotic pressure of larger blood proteins. So this, the difference between the osmotic pressure in the capillaries minus the osmotic pressure in the interstitial fluid, tends to be the forces that draw fluid into the capillaries. Okay, so what you'll notice is the oncotic pressure, the difference between the oncotic pressure in the capillaries and the interstitial fluid actually stays fairly constant. It's about 22 millimeters of mercury. And you can see 22 to 25. You can see it stays constant throughout the length of the capillaries. But the hydrostatic pressure in the capillaries plummets across the length of the capillaries. It's very high in the beginning of the capillary beds, about 36 millimeters of mercury, but then it gets very low, that pressure, at the end of the capillary beds. So what that tends to do, take a look at this bottom figure here, it tends to cause net filtration in the beginning of the capillary beds. You get a lot of fluid and solutes that are forced out. And at the end of the capillary beds, you get net absorption. But only about 9/10 of the fluid is actually reabsorbed. So there's this slight mismatch. And the lymphatic system, remember that secondary system that I talked about, the lymphatic system? One of the primary roles of the lymph system is to return that last 1/10 of the fluid back to the circulatory system. It actually takes that last 1/10 that's not reabsorbed and it returns it back to the circulatory system. So, all right, I'm going to get out of this one. All right, hopefully all right. Play this animation for you.
At the arterial end of the capillary, the net filtration pressure is equal to the net hydrostatic pressure minus the net osmotic pressure. The net filtration pressure is 13 millimeters of mercury. This causes fluid to move from the capillary into the interstitial fluid. At the venous end of the capillary, the net filtration pressure is equal to the net hydrostatic pressure minus the net osmotic pressure. The net filtration pressure is minus 7 millimeters of mercury. This causes fluid to move from the interstitial fluid into the capillary. Approximately 9/10 of the fluid that leaves the capillary at its arterial end re-enters the capillary at the venous end. About 1/10 of the fluid passes into the lymphatic capillaries and returns to the bloodstream via the lymphatic system.
All right, pretty much just a
At the arterial end of the capillary.
Okay. Okay, so when you calculate net filtration pressure, I'm either going to give you the net pressure, which means the hydrostatic pressure has already been subtracted out. The net, basically the hydrostatic pressure in the capillaries minus the hydrostatic pressure in the interstitial fluid has already been subtracted. That would be the net hydrostatic pressure. Or I'm going to give you both, all of the parameters. Oncotic pressure is, again, the osmotic pressure of the larger blood proteins in the capillaries and in the interstitial fluid. So I'll go back to that particular, right? Here's the equation. Again, it's on the back of your sheet. You don't have to memorize this. Here's the take-home message, so please write this down. If the net filtration pressure is a positive number, then you're going to get filtration. If the net filtration pressure is a negative number, then you're going to get absorption. So now you can predict which way the fluid is moving. Say that one more time. That's an important concept. If once you calculate the net filtration pressure, if it's a positive number, filtration will occur. If it's a negative number, then absorption will occur. All right, so we're almost done here. I've got one more concept. Let me just finish this up though. The lymph system, again, is very important in that it returns that last 1/10 of the fluid that's filtrated. It returns it back to the circulatory system. And you know that's true. Some of you might are aware of this. This is called elephantiasis. It's actually caused by a filarial worm that blocks the lymph system. Wuchereria is the genus. So this is a filarial worm that blocks the lymph system, and when that occurs, your body, the lymph system can't return that last 1/10 of the fluid, and edema happens. It's a buildup of interstitial fluid. So it's a good example of the role of the lymph system. All right, veins act as a volume reservoir. They're very floppy. They have a very compliant wall. That means small changes in pressure translates to huge changes in volume. So small increases in blood pressure lead to large changes in volume. What that means is about 60% of your blood is actually pooling in your veins. There's no elastic property to keep the blood moving. What usually occurs is in the veins you have one-way valves to make sure that the blood keeps moving in a unidirectional way. And you have to use your skeletal muscle and your respiratory, when you just breathe in and out, your respiratory muscles actually help return blood to your heart, which is kind of interesting. Okay. All right, so this shows you right here, skeletal muscle and your respiratory muscles help to return blood to your heart. Okay, so finally, this is the last thing I want to talk about is baroreceptors. This is a really nice concept to have under your belt. It is a great control system. And what it says is you actually have these sensors in your carotid artery, it's in your neck here, and the aorta, the aortic arch. And it is monitoring your blood pressure. What it does is if the blood pressure gets too high, it actually sends a signal to your cardiovascular control center to initiate a parasympathetic response. So it slows your heart rate, it decreases cardiac output, and in effect it decreases mean arterial pressure to bring your blood pressure back down to normal. So you can see here's the normal resting value. If your blood pressure gets too high, then it increases the baroreceptor firing rate. Those are the neurons that are coming from those sensors. And it triggers a response from your cardiovascular control center in the medulla oblongata, in your brain. And it initiates a parasympathetic response, slowing heart rate, decreasing cardiac output, and decreasing mean arterial pressure. On the opposite extreme, if your blood pressure falls, right, to levels that are out of range, it decreases the baroreceptor firing rate, and that decreases parasympathetic response and increases a sympathetic response. This is why patients that may go into the ER hemorrhaging, like say a gunshot or knife wound, and they're losing blood, they may have a sympathetic surge anxiety, right? Sometimes they'll need to be strapped down, right? That's a sympathetic surge. It's a physiological response. Some people also think about it as shock, right? To try to increase heart rate, increase stroke volume, increase cardiac output, and increase mean arterial pressure. What's the problem with that? Yes, exactly, losing more blood. If you're hemorrhaging and you have this sympathetic response, you're going to lose blood faster. So you need to put a tourniquet on that quickly. All right, I'm going to leave it there. That's the end of the lecture, everyone. Let's go ahead and play our game here. Okay, so this is a game I discovered more or less recently, but I don't know if you all have played Kahoot before. Yes! Okay, so you'll be able to see the winners on here. There's 15 questions, and I do have prizes. So the top 3 people will actually get candy for their entire table. Yes. All right, so let's go ahead and play. Yes? Are we working? You can work as a table, but here's how this works. What happens is you have the team or the person that has the right answers, the most right answers in the quickest time. So you can discuss it, but you have to do it very quickly. Those people are going to be at the top of the leaderboard, okay? All right, so keep it clean, everybody. I didn't put any. All right, so here, join, ready? Yeah, here we go. You want to join either at kahoot.it or with the Kahoot app. Either way, I'll give you some time here. You can see everybody's names are coming up. We got 58 players today. Okay, we're all the way up to 67, which is great. All right. Wow, we're doing great. All right, looks like we topped out at 82, which is fantastic. Oh, we're up to 85 actually. Okay. All right, I'm going to go ahead and start it now. Oh, okay, hold on. Oops. All right. Number 1, muscle cells can also be called muscle fibers, myofibers, motor units, or none of the above. All right. All right. All right, let's see. Do they show us your leaderboard yet? I don't. Oh, they do, huh? Okay, all right. Renee is up front here. Okay, so next one. Quiz. The neurotransmitter released into the synaptic cleft by a motor neuron is serotonin, norepinephrine, acetylcholine, or dopamine. We're doing great. Renee's still at the top. Wow. All right, let's keep going here. End plate potentials in motor neurons. Motor end plates are braided potentials, action potentials, equilibrium potentials, or resting membrane potentials. Doing great here. Nice. All right. Ayush and Isra are leading right behind Renee. Let's see if they can catch up. Dihydropyridine receptors are voltage-gated sodium channels, voltage-gated potassium channels, nicotinic acetylcholine receptors, or voltage-gated calcium channels. All right, a little bit harder. They are voltage-gated calcium channels. Now, in skeletal muscle, they don't conduct calcium. They're actually physically coupled to ryanodine receptors, but in the heart, they do conduct calcium. It's a calcium-induced calcium response. All right, good job. Let's see who's... Renee's still on top. All right. In skeletal muscle, after calcium is released from the SR, it then binds to which molecule to initiate muscle contraction? Is it tropomyosin, troponin C, troponin T, or myosin light chain kinase? All right, ooh, a little tougher. It is troponin C. Good job. Remember, the C is for calcium, right? Calcium binds to troponin C. And then it moves the tropomyosin out of the way, revealing the actin and myosin binding sites. All right. Renee's still on top. Rachel's second now. During skeletal muscle contraction, and specifically during cross-bridge cycling, ATP is important because it causes the power stroke, causes myosin actin to dissociate from each other, causes tropomyosin to move, exposing the actin-myosin binding sites, or re-energizes the cross-bridge myosin head. Nice job. 36 of you got that right. So remember, ATP is important in the dissociation of myosin and actin. Again, we talked about rigor mortis. When there's no ATP in your cell after death, it causes persistent contraction. All right. Renee's still on top. Rachel's right behind, and Sherry's in third. Skeletal muscle characterized by a few number of myofibrils in parallel, but very few, a large number of myofibrils, but very few myoglobin and mitochondria. Slow oxidative, fast oxidative, slow glycolytic, or fast glycolytic. Large number of myofibrils, but very few myoglobin molecules and mitochondria. Nice job. There's the fast glycolytic. Yes, so fast glycolytic, they're very powerful, but they fatigue very easily. Fatigue very easily. All right, Renee's still on top. Rachel and Kaylee are right up behind. Okay, blank relates to the strength of an isometric contraction to the length of the muscle at which the contraction occurs. Is this intensity force, frequency force, length, tension, or load velocity? Length relates to the strength of an isometric contraction to the length of the muscle at which contraction occurs. Okay, good job. Most of you got that right. It of course is the length-tension relationship. This is also called preload. Anything that sets the length of the muscle prior to stimulation is preload. All right. Rachel, Emily, and Liv, top three. An ECG shows an R to R value of 1 second. Now you might have to make a calculation. What is the heart rate? An ECG shows an R to R value of 1 second. What is the patient's heart rate in beats per minute? 40, 60, 75, or 90? Okay, so what it would be is 1 beat per 1 second, and then when you change that to beats per minute, you just multiply by 60, right? So that would be 60B. Good job. So again, the R to R value is 1 second. It'd be 1 beat per 1 second, and you just have to convert that to beats per minute. All right, doing great. Number 10. This is going to be on your exam. It might not be P wave, but it's going to be one of them. The P wave is a summation wave generated by the depolarization of the atria, the depolarization of the ventricles, the repolarization of the atria, or the repolarization of the ventricles. What is the P wave? All right, that's right. It is atrial depolarization. All right, the QRS is ventricular depolarization, and the T wave is ventricular repolarization. So one of those is going to be on the exam. One of those questions will be on the exam. All right, Rachel's still on top here. Good job. Sympathetic nervous system stimulation causes an increase in heart rate, an increase in cardiac output, an increase in mean arterial pressure, or all of the above. Nice job, all of the above. All right, so remember, when you get sympathetic nervous system stimulation, this is a GS-coupled response. GS-coupled response increases cyclic AMP, which binds to the funny channels, which increases the slope of phase 4. That increases heart rate. It also has effects on titin. It has effects on titin and phospholamban, actually. So you get an increase in stroke volume as well. Increase in stroke volume and a faster relaxation. You get an increase in heart rate, increase in stroke volume. That would lead to because you multiply it together, that would lead to an increase in cardiac output. And assuming that total peripheral resistance stays the same, that increases mean arterial pressure as well. So, Rachel, still holding on to the top spot. Emily's second. Julia is third. All right, 3 more. That's all we got, 3 more. Phase 4 of the SA nodal action potential waveform is due to voltage-gated calcium channels, funny channels, voltage-gated potassium channels, or voltage-gated sodium channels. We're talking about phase 4 here, right here, phase 4. All right, nice job. They are the funny channels, right? So those are the hyperpolarization cyclic nucleotide gated channels, okay? Those are the funny channels. They are part of the pacemaker cells. They're expressed in pacemaker cells. All right, good job. Rachel's still doing great. 13, during the ejection phase of the cardiac cycle, ventricular systole, which heart valves are open during the ejection phase? The right-left AV valves, the tricuspid and bicuspid valves, the pulmonary and aortic semilunar valves, or none of the valves are open. Nice job. Okay. So if you didn't catch that, the right and left AV valves are exactly the same as the tricuspid and bicuspid valves. So this is the exact same. The right answer is the pulmonary and aortic semilunar valves. During ventricular systole, the ventricles are contracting and the pressure in the ventricle is higher than the aorta. So you know that blood is being forced out into the aorta through the pulmonary and aortic semilunar valves. All right, let's see here. Okay, Mary's catching up. Look, she's on fire. Okay, Rachel, Emily, and Mary. 14 out of 15. Preload in the heart is best described by the Frank-Starling mechanism, a concept most related to intensity force, frequency force, length tension, or load velocity. Preload, Frank-Starling mechanism. All right. Looks like we were kind of all across the board on this one, but yes, 28 of you got that right. It is the length-tension relationship. So let me explain this. The more blood that you force into the ventricle, remember end diastolic volume, the more it stretches the muscle, the cardiac muscle, towards optimal length, optimizing the actin-myosin cross bridges and giving you a more forceful contraction. That is the length-tension relationship. That blood that's being forced into the ventricle is setting the length prior to stimulation. All right, that's called preload. And I think, Rachel, you're still on top here. Emily, and then Mary. I think this is our last one. Yes, this is the last one. In relation to other blood vessels, the velocity in the capillaries is higher than the velocity in the arteries, higher than velocity in the veins, lower than the velocity in both arteries and veins, the same throughout the entire circulatory system. Yes, good job. It's lower than the velocity in both the arteries and the veins. It slows down tremendously in the capillaries to allow enough time for oxygen and nutrients. Drum roll, please. Drum roll. And the top three are Rachel, Emily, and Brady Cardia. Nice. That's a great name. All right, so raise your hand. Top three. Where's Rachel? Yes, all right. Okay, so let me see here. Okay, let's see. Congratulations. Also, I do have a worksheet. Let's see, we do have a little bit of time. No, I'll let you guys go. You can fill this out. This will also help you. And don't forget to turn in your essential cardiovascular sheet. I'll put this up here for you guys to study. And that's it. Remember the review session today. Congratulations to our tables. Oh, sorry. Good job. Rachel, you get first choice. We got Snickers, we've got Reese's, or we got Kit Kats. Reese's, all right. And then Emily, yes, you want Snickers? Brady Cardia. You get Kit Kats. Yes. Congratulations.
I have a question on this worksheet actually about how is pulmonary vascular resistance calculated?
Yes.
I was confused on which equation we used.
Okay, yeah. So it's Ohm's law.
Okay.
It's not on the back sheet, but remember it's going to be the pressure gradient is going to be equal to cardiac output, which you've already calculated, 5,250.
Yeah.
And then you're looking for total peripheral resistance. I'm sorry, the resistance through the pulmonary circulation.
Okay.
So the the pressure gradient, you want to try to isolate it from basically the pulmonary arteries minus the pulmonary veins.
Okay.
And you do have pulmonary arterial pressure.
Okay.
But you don't have the pulmonary venous pressure. You only have left atrium. So the best one is the pulmonary artery pressure minus the left atrium pressure.
Okay.
That's going to give you the pressure gradient, and then you just use cardiac output, and now you can calculate the resistance through the pulmonary circulation.
Okay. That's what I was kind of trying to do, but I saw some people that multiplied it by the heart rate. And I don't know why.
Oh, maybe they shouldn't have, really, because they've already calculated heart rate times stroke volume to get cardiac output.
Oh,
yeah,
that makes sense.
Yes.
Okay,
yeah.
thank you.
Yeah, you're welcome. Oh, hi. Hold on.
Okay.
So I did the worksheet on my iPad.
Sure.
So is that okay if I just
Yeah.
email that to Megna?
Megna,
then? Okay.
yes, perfect.
Okay, thank you.
Yeah, you're welcome. Hi.
Okay, so you know how I was supposed to do it after class? On
Yeah.
Is it gonna be the same but on Wednesday?
Yeah,
Okay, so
Yeah.
Wednesday at 2?
that sounds great. We can
Okay.
do that.
All right.
I'll
perfect.
put that on my calendar and send you an invite. Okay,
All
sounds
right,
great.
Sounds good.
I had emailed you about taking a test today.
Yeah.
Does that still work?
Yeah, that'll be fine. Can you still do it around 3 though?
It would be at 3:30 because I have
Okay.
meetings. Otherwise, I could do it Tuesday in the morning, like around 8.
Tuesday in the morning would be fine. I could meet you at 8.
Okay.
The thing is I have the review session at 4.
Okay.
Yeah, so I
Yeah,
won't be
I
able to do that this afternoon. Sorry.
Okay.
Yeah.
No, that's okay.
And I only organize that on Friday, so.
Okay.
Okay, so let's do 8 o'clock tomorrow.
Okay, sounds
That's
good.
not-
And
oh
then
wait, I can't do 8 o'clock tomorrow. Actually.
okay.
Yes. What time do you have tomorrow? What time other than 8?
I could do after 4:30. I don't know if that's too late.
That works.
Okay.
Yeah, I have a class until 4.
Okay.
And I can just meet you after that. Does
Okay.
that sound okay?
Yes, that's
okay.
perfect. And then,
Send me an email and I'll send you a calendar invite.
Okay,
Yeah,
sounds good.
okay.
And will we be meeting in this room?
Probably in my office.
Okay.
Yeah.
Sounds good.
Sounds
Thank
good.
you.
Yeah, thank you. Hi.
I had a question. I couldn't quite get it down. Is this so? This is due to